So just because I know that composition can be a little hairy sometimes. All right, so we had just done one composition last time, and we noticed that f of g is not always going to be the same as g of f, right? Almost like hardly kind of ever, sort of, if you think of all the different combinations of functions you could choose from. It has to come from a specific type of function that gives you that kind of same answer, and that's what we'll talk about in the next section some. So let's just first do some more compositions though. So if we have f of x is equal to 6x plus 2 and g of x is equal to 4 over x plus 2, we're going to find f of g of x. So what does that mean again? Well, is this multiplication? No, it's composition. Yeah, we treat g of x, like the input, in f. So that means we have f of g of x, right? Or then you can continue on and think, well, g of x is really 4 over x plus 2, right? We're plugging that in to f, right? So then what does that look like? How do we plug that into f?
6, 4x plus 2.
6, and then this, the input, 4 over x plus 2. Plus 2. Yeah, we just replaced x. So now what? Simplify it, right? We have to multiply the 6 and the 4, because remember to think about that 6 is over 1. So then we get 6 times 4 is 24 over x plus 2. Now then, what do we do with this 2? It's over 1, so we want it to be, though, x plus 2 in the bottom, common denominators. So we multiply by x plus 2 over x plus 2, right? Okay, so then what do we get? We have 24 here over x plus 2 plus what? 2x plus 4 over x plus 2. And then combine like terms. Yeah. So that means we have 2x plus 28 over x plus 2. Is that a final answer? Not for my math lab. What do we have to do to finalize it? Factor the top if you can. It's not always going to be possible, but in this case it is. So I'm going to write it up top here. Our final answer, so this is equal to 2 factored out of x plus 14 over x plus 2. In that, nothing can be canceled, nothing can be factored further. It is fully simplified. That's as far as we can go with it. Right? Okay. So are we good on that one? Yeah. Any questions? Because I know there's quite a few like this one in the homework. Okay. Let's do another one. So if we have f of x is equal to 10 over x plus 1, and g of x is the square root of x plus 19. We want to find f of g of -3. So how do we do that?
Is this the rule that you told me?
I'm sorry?
The thing where you plug in -3 to G first.
Yes, we plug -3 into G, and then whatever we get from that, we plug into F, right? So let's write it out in that formatting, what we just said, right? So that means we're doing F of G of -3, right? So we're plugging -3 into G. Then whatever we get there, we plug into F. So let's find G of -3. G of -3 equals, what do we do?
So, square root
The square root of, yep.
-3 plus 19 equals 16.
The square root of 16.
Which equals 4.
Yay, 4. Okay. Now what? So now we know that G of -3 is 4, right?
Plugging 4 to F.
So F of 4. Yeah, that's what we want to find now. So just plug it in, right? So that means we have 10 over 4 plus 1, or 10 over 5, yep, which is 2. So 2 is our final answer, okay? Because, let's go back to what we did. We were asked for F of G of -3. So, instead of finding F of G and then plugging -3 into it, we found -3 plugged into the inner function, which was G, figured out what that was. We got 4. Okay, then we took 4 and plugged it into F, figured out what that was. And that's our outer function answer. So that's the final answer of the composition. Okay? All right. Let's do another one of those. So we're going to do F of x is equal to x minus 5. G of x is equal to square root of x plus 3. And we want to find G of f of 2. So, on that one, we kind of separated it out and then came back in. We're going to do it just kind of cohesively, all as one kind of calculation, I guess you could call it. This time just showing another way you could write it out. Okay? So, we know that this means we want to find G of f of 2, right? So that means we're plugging 2 into f, which is x minus 5, or in this case, 2 minus 5, right? That's what f is when we plug 2 into it. So let's simplify that. That means we have G of -3, right? Okay, well now let's just plug -3 into G. So G of -3 is equal to, well, the square root of -3 plus 3, which is the square root of 0, which is 0. So do you see how we kind of did that as all one calculation? Instead of, oh, well, let's find G of -3, jump out, find that. Go back, plug it in, solve. This time we just put it right here where it was, right? It's the same calculations, just all together, kind of. Okay? Because sometimes when we do it that way, we just want to stop at the 4 because we have an answer, right? And then we forget to fully finish and find the final answer. Okay? That's all I have for 3.5. So, were there any questions from homework, problems, or anything like that from 3.5 that anyone had? No, we're good? More or less? Okay. Then let's move on to 3.6. 3.6 is one-to-one and inverse functions. we'll first start off with the definition. So, a function is one-to-one. You can write it out, 1 to 1 kind of thing, or just write it this way. If for any values a not equal to b, so basically I'm saying different values, okay, in the domain. So for any different x values, then f of a does not equal f of b. So that means, essentially, right, if we have different x values, then they have to give us different y values. Does that make sense? Okay. So let's look at an example. If we look at f of x equals x squared, our nice fallback. So if we look at this function, what we're seeing here is we have two different x values. However, they give us the same y, right? Or what we're saying is f of 2 equals 4, which also equals f of negative 2, right? Because if we plug 2 or negative 2 in to x squared, we get 4 for both of them, right? But obviously 2 does not equal negative 2. Okay? So we have different x values that gave us the same y value. That means this function is not one-to-one. Okay? Another way you can see this, if we're looking at a graph, is does it pass the horizontal line test? Okay? So to be a function, it has to pass the vertical line test. To be one-to-one, it has to pass the horizontal line test. Okay? Question? Yeah.
Wait, but doesn't it pass the horizontal line test? I don't get it.
Well, think about what we said for a vertical line test. If the line collides kind of thing or hits two different points of the graph, it's not a function, right? So the horizontal line hits two different points of the graph. So that means it's not one-to-one. Okay? All right. So let's look at a few others. If we look at the square root of x, what's that graph look like? Yes, just like that. A side swoop. Very technical, right? Side swoop. Okay, so does this pass the horizontal line test? Yes. We can draw a whole bunch, right? Anywhere along here, it passes. It's all good because it does not touch the graph in multiple places. Okay, what about x cubed? What does that look like? Yes. Well, technically you want to think about it from left to right, right? But yes. Okay. So does this pass the horizontal line test? Yeah. Yes. Again, we can draw horizontally and not hit the graph multiple times. So it's good. What about the cube root? It's the sideways version of this, right? this pass the horizontal line test? Again, yes. So far all of these functions have been one-to-one, right? What about the absolute value function? What does that look like? A V. And it doesn't, because it's almost the exact same graph look-wise as x squared, right? It's just flat instead of curvy. So that means there's a whole bunch of times that it doesn't pass the horizontal line test. What about 1 over x? What does C look like? Yeah, the two individual things. Does that pass the horizontal line test?
Yes.
Yes, because here, where it kind of makes you think it might not, that's an asymptote, right? It never reaches that point on either side. So that means it doesn't ever quite overlap. So that is also a yes. So out of our kind of main parent functions that we look at, we only have two that are not one-to-one. X squared and absolute value of x, right? Because x squared and the absolute value kind of negate having a negative inside, right? You have a negative inside, it gives you the same thing as a positive does, right? Not always necessarily the same values, because what if we have a other number in there, right? A horizontal shift or something, but it's the idea, right? So why do we care about this though? What does one-to-one do for us? One-to-one tells us whether or not a function has an inverse. An inverse specifically that is a function. Okay? So, we have another definition. So, f is a one-to-one function with domain A and range B. So that means the inverse of f, written f to the -1, okay, has domain B and range A. So, essentially, f inverse switches the x and y values. Okay? Whatever was an x or domain is now a y or range, and whatever was y or range is now an x or domain. Okay? So, let's just fully write that out. The domain of f is the range of f inverse. The range of f is the domain of f inverse. Then, if AB is on F, then BA is on F inverse. So essentially, we literally flip the point around, right? So if 3, 2 is on F, then 2, 3 is on F inverse. Okay? Now, super, super, super important to remember. F inverse of x is not 1 over f of x. This is the only time that a negative exponent kind of thing does not mean put it in the denominator, because this isn't an exponent. Okay, it is just a kind of function notation way of saying inverse. Does that make sense? I just realized I forgot to turn. Whatever. Okay. So, just please don't do that. Okay? So, let's do an example. There is one specific that is in the homework that can be a little troublesome. So, if we're given a graph and it looks like that, and we want to find its inverse. So if this is f of x, we want to find f inverse. Okay? So let's write down what we know about f and then change it to be about f inverse. Okay? So these are f of x facts. And then we'll have a list of f inverse of x facts. Okay? So, let's write out the points. And then we'll do the domain and the range. Okay? So, what are some points on f of x? 0, 2. And another one, 1, 3, and 2, 6. Right? So what are those points when they are translated to being the inverse points? 2, 0, 3, 1, and 6, 2. They've just flipped, right? So let's plot those. We have 2, 0, 3, 1, and 6, 2. Okay. Now let's figure out our domain and range of f. So what's the domain of the original function? What can we plug in? Not based on the points, but based on the graph. Starting at 0 and going to?
I'm sorry, 2. 6, 0, 5.
Infinity. It's an arrow. It goes forever.
Oh, I was looking at
Can we plug in 0?
that.
Yeah, so it gets a bracket. What about range? What can we get out of f of x? 2 to infinity with a bracket. So, what's the domain of f inverse?
Same.
2 to infinity. Not the same, they flip, remember. Gotta exchange them essentially, right? The range becomes the domain, so it's 2 to infinity, and the domain becomes the range, so it's 0 to infinity. And it makes sense on the graph that we just did, right? The domain starts at 2 and goes forever, right? The range now starts at 0 and goes up forever. Slowly up, but up, right? Does this make sense? Okay. One thing that I want you to recognize here is to visually kind of see an inverse function. It is just flipped around the y equals x line. Okay? It's actually really cool if we had graph paper. This is how I learned about inverse functions. and we drew a graph, folded it along the y equals x line, and then put like push pins through points on the original function, it would push through the paper on the points of f inverse. So if we folded this right here, this point would match up here, this point would match here, and this point would match here. So it's a really good like visual exercise. But I don't have graph paper for everyone. I can certainly bring it next time if you want me to, but I didn't bring it this time. Okay? So are we good on that problem? Yeah? Okay, because there is one really similar to this where you have kind of pieces of different graphs, like a piecewise function, but then you have to invert. Okay? Now, one thing I want you to just recognize, this is not a reflection, okay? We're not flipping it around the x or y axis like we were in 3.4, okay? This is the inversion, so it is kind of a mirror image around y equals x, but it's not the same thing, okay? All right, so now another way, if we don't necessarily have a graph to invert, there is a way of finding the inverse function from the original function itself, okay? And it's a pretty simple 4-step process. So, if we have, sorry, I just jumped ahead of myself. I actually wanted to do something else first, okay? I want to look at composition of inverse functions really quick first. So, if we have f of x equals 4/7 x minus 3, and we have g of x equals 7x plus 21 over 4. We want to find both g of f and f of g. So we're going to compose them both ways. So let's find f of g of x first. Okay? So when we do this, we get f of g, which is 7x plus 21 over 4, which is really 4/7 times 7x plus 21 over 4 minus 3, right? So we took f and replaced x with g. Now let's simplify this mess. We have 4 over 4, essentially, right? So we can cancel those. We can also take a 7 out, because this term has a 7. This term also has part of it's a 7, right? We can take a 7 out and we're left with a 3. So that 7 cancels, because we canceled it out of both pieces of the numerator. Yes? Okay. So then, this term is just x plus 3, but then we have that minus 3 still. So overall, f of g is equal to x. Okay? Now let's find g of f. So that will be g of 4/7 x minus 3, which is 7 times 4 over 7x minus 3 plus 21 all over 4, right? Okay, So, let's simplify. When we multiply this 7 times 4 sevenths, it's just 4. 4x, technically, but yes. 7 times minus 3, minus 21, and then still plus 21, all over 4. So then the 21s cancel. We're left with 4x over 4, which is x. Huh, we got x for both of these. That's kind of strange, right? We're supposed to, because I want us to go back to this now and think about something. If we plug in, right, or think about plugging in a number into f, right? If we plug 0 into f, and then plug, well, what do we get? 0 into f gives us 0 into f gives us 2. 2 into f inverse gives us 0. It takes us back, right? So, I want us to notice this. If we plug an inverse function into its function, we get back x. We get back what we plugged in, because we plugged in x, right? So then if we do the opposite, we plug the function into its inverse, we also get back x. We didn't until we got x both times. Now, it has to be both ways. You have to get exactly x when you do f of g and g of f. If you get negative x or anything else, it's not an inverse. If we got negative x the first time, we can stop because we already know it's not the inverse. Doesn't matter what the other one gives us. If one of them doesn't give you x, done. I would check it just to make sure, right? But it just means they're not inverses. And there are plenty of functions that are inverses of each other, right? And they're not always going to be full inverses of each other.
So you could just say f of g equals g of f?
Yeah. And I would technically then say equals x, right? Any questions on that? All right, let's practice this a few more times. So, actually now we're going into what I was saying before, that if we're just given a function, we can find its inverse by 4 steps, okay? So if we're given a 1-to-1 function, f of x, and we can find the inverse function, by first writing y for f of x, then switching the x's and y's, then solving for y, and then writing f inverse of x for y. Okay, so essentially write it with y's and x's, then switch them, resolve it for y, and then write it back into function notation. Okay? So now let's do an example. If we're given f of x is equal to the cube root of x minus 5, and we want to find f inverse of x. So, first step, we write it as y equals the cube root of x minus 5. Then, we switch the y's and x's. So, x equals the cube root of y minus 5. Now we want to solve for y. What do? What's our first step?
Get rid of the third.
Put it to the third, get rid of the
Square
root, right? So we cube both sides. The cube root and cube cancel. They're inverses of each other. Sorry, I had to. So we have then x cubed is equal to y minus 5, right? Then add 5. So y is equal to x cubed plus 5. To fully finish, f inverse of x is equal to x cubed plus 5. Yes?
So, oh, I see what you did. I was like confused as to why the y would be negative and the x, but I saw that you did that.
I just switched which side I wrote y on. Yeah. Okay. How could I check this? How could we check this? Plug it in. Compose them, just like we did with f and g, right? If we find that f of f inverse and f inverse of f both give us x, then we solved it right. Okay, so if you're ever questioning if you did the algebra correct, you can always plug them into each other. Generally, if you want to do a quick check, you could plug one in, right, to the other, and if you get x, that's usually going to be a good indication, because if you made a mistake, you're not likely to get x either way, but it's not foolproof, right? Technically, we would have to get x both ways to 100% know that it's the inverse function, okay? But a quick check would just be doing one. All right, let's do another. So if we're given f of x is equal to 3x minus 4 over 2 minus x, and we want to again find f inverse, what do we do first? Put in the y. So y is equal to 3x minus 4 over 2 minus x. And then switch them. X equals 3y minus 4 over 2 minus y. Now what? Solve it. However, we have y's in multiple places. What do? We really don't like that this y is in the denominator, so let's move it. How do we move something out of the denominator? Multiply by it, right? We want to multiply both sides by 2 minus y. So these cancel, so then we're left with x times 2 minus y. I just flipped them because generally we write the single term thing in front. It's not incorrect to write it the other way, it's just generally we see it this way. Equals 3y minus 4. Now what? How do we get that y over with the other y? Dilemma. We have to distribute that x. The only way to move that y is to give it more stuff before we can move it. We have to make it not multiplied by something. So go ahead and multiply it out. That's fine. This one's a 3y. Does that make it bad? Not exactly what we want to end up with, but it's not bad, right? Just because it's xy doesn't change it from 3y. So then that will be 2x minus xy is equal to 3y minus 4, right? So then, what? Add the xy, get the y terms on the same side. So we have 2x equals xy plus 3y minus 4. Now what? We can factor out the y just from these terms, right? This term doesn't have a y. What do we want to do with that term then? Move it to the other side, because we don't want it with the y stuff. So let's do that first. We have 2x plus 4 equals xy plus 3y. Now we can factor, right? So we have 2x plus 4 equals y times x plus 3. Now what? We divide this term because these are multiplying. We have to divide, right? You have to undo what's being done to the y. So y is now equal to 2x plus 4 over x plus 3. If your original function looked something like this, most likely, almost always, your inverse function is going to have the same kind of look to it.
Okay, what happened in the end?
I divided and just wrote it the opposite direction. Just because we always see it as y equals instead of stuff equals y. Okay? So we had to distribute to then end up factoring. We basically had to do stuff, right? We multiplied, distributed, then moved stuff around, factored, and then divided. So we literally just kept undoing what we had done early on, right? You end up doing that a lot when you solve for inverses. Okay? So now we want to think about the domain and range of these functions without the graph. So, easiest way is to think about the domain, right? We can do domains. Thinking about ranges, coming up with the range without having the graph is not easy, right? So, let's find the domain of f. Because what's the domain of f? The range of f inverse, right? So this is the range of f inverse. So by finding the domain of f, we'll find the range of f inverse. If we find the domain of f inverse, we'll find the range of f, right? So if we can find the two domains, we found the two ranges. They're just opposites. Okay? So let's think about the domain of f. So we're looking at this function here. What don't we like? First, what type of function is it? Rational. So what don't we like about rationals? The denominator. The denominator cannot equal 0. So that means x cannot equal 2. Right? So what is the domain then? Negative infinity to 2, then 2 to infinity. All with parentheses, right? Okay, now let's think about the domain of f inverse, which is the range of f. So, what type of function is f inverse? Rational again. And we don't want x plus 3 to equal 0. So that means x can't equal -3. How do we write that out in interval notation? -infinity to -3, and then -3 to infinity. So, domain of f is -infinity to 2, 2 to infinity. Range of f is -infinity to -3, -3 to infinity. And then they just switch for f inverse, right? So, essentially, find your two domains, and you have your ranges, right? They just switch, and they're for the other one.
I mean, the ranges are flipped.
Yes. Yeah. Find your domains, and then flip them to the opposite function for your range. Yeah. I said that right, didn't I?
Mm-hmm.
Yes. Okay. Sometimes I lose myself when I say things. Okay. All right. So we basically figured out one-to-one, right? That just means that the function can't overlap horizontally. If it does, when we flip it, so let's go back to our original function that we said if it was 1-to-1, x squared. If we were to flip that around the y equals x line, what that then looks like is, you see how that's the flip, right? If we kind of tilt that over, this function now is not, or this equation is not a function, right? Because it doesn't pass the vertical line test. If you flip the horizontal line around y equals x, that gives you that vertical line. So essentially what we're saying is, if a function does not pass the horizontal line test, it's not 1-to-1, that means its inverse is not a function, because it won't pass the vertical line test. Okay? That's the whole idea of this. So if a function does not pass the horizontal line test, its inverse will not pass the vertical line test, which means it's not a function. Okay? So only 1-to-1 functions have function inverses. Okay? That's why when we look at this sideways parabola, technically that would be y equals square root of x and y equals negative square root of x. We split it into those two pieces. Okay? All right. So that is the end of 3.6 and the end of chapter 3 actually. So on Thursday we will start on chapter 4. Okay? So, quiz tomorrow on 3.4.3.5, which is on what topics? 3.4 is transformations. So, moving it, right? Shifting it back and forth or up and down. Reflecting it, stretching and compressing. Then 3.5 is algebra functions and composition. Okay? So we're doing a lot of graph things and function things, essentially now. Okay. See you tomorrow. Oh, really, sorry, one quick thing. I know that the last day to withdraw is this Friday, right? Without getting an F or anything added to the W. Please don't just withdraw without talking to me first, okay? Because you don't know what's happening throughout the rest of the course. Okay? So at least talk to me if you're worried. Thanks, right? I ordered them specifically because saw an ad on Facebook, and I really hate Facebook because they keep showing me really good ads. And yeah, I kind of just had to get them because I was teaching college algebra this semester. So yeah. Let me stop this.